I want to illustrate the use of LB2D prime for the simulation of capillary rise. Let's begin by looking at the flags file, flags.h in the src directory. And we'll start at the top here. So what's going to be important for this single component multiphase is we should have one fluid component, everything else so far should be off. The store U composite is on. It's not absolutely critical at the moment. Compute on solids is on, but it shouldn't be critical. This is critical, however. Non-local forces, both the single component multiphase phase separation and the adhesion to the surface will rely on having a 1 here. And probably that's all that we need to worry about. Okay, so I'll save this, and then we'll need to make, since we may have made some modifications to the H file, and then let's choose a new input file, a new BMP solids file, and I've already created one called 100 by 100, and we can do this with bitmap or Windows Paint. And right now I have something that looks like this. And the rationale behind this is that we're going to put a fluid in the outside area here. It's going to fill up partially. We'll talk about that when we look at the params.in file. And on the bottom, we're going to impose a gravitational field on the whole thing pointed downwards. So we need some walls on the bottom to hold it back. This is about a, I believe it's 14 wide. Oops. Yeah, that's right. It's a 14 wide slit in 2 dimensions. So, based on some calculations I've made, that should give us about a 50 lattice unit capillary rise in order to match a bond number comparable to the one that we have in the book, which is about 7.36 times 10 to the minus 3. Oh, sorry, that's not the bond number. The bond number is 1 over 7.36. Please refer to the book for more information about this particular problem and the scaling that we're doing back to the real world. Okay, and the last thing to do is set up the params.in file. So of course it has to be 100 by 100. This characteristic length would only be used to compute the Reynolds number. Not really relevant right now. I want to reduce this because I don't want to wait very long to run this. Tau 0 will leave a 1. And this is the value that I've computed based on the bond number to give similarity to a real-world capillary case. Anything that has to do with substance 1 won't be needed. Buoyancy is not relevant here, nor are these. But the rho A and the rho B are. This is approximately the equilibrium liquid density and approximately the equilibrium vapor density. Anything having to do with rho sigma or sigma will not be used, nor will any of these. However, these two are critical. This is the one that controls the single component multiphase phase separation. Basically, it's like the temperature and controls the equation of state that's relevant. And then this one is the one that controls the strength of adsorption or the contact angle. And in our case, it's going to be for a contact angle of 0. Proceeding down, none of these are really relevant. All the pressure and velocity boundaries are turned off. These zero concentration gradients have to do with the sigma component. It's not relevant. But this is relevant. We have an initial condition of 8, which is a rectangle. And down here we use the relative values. So in the y direction we go from 0 to 1/4. And in the x direction from 0 to 1. That is a rectangular on the bottom quarter of the domain. That will be from 0 to 25 lattice units up, filled with rho A. And rho B would occupy the rest of the domain. And that's all we need here. Now let me start the code, and immediately I will bring in the output files. So here's the initial condition. As we said, a quarter of the domain filled with dense fluid. The capillary is here. And we should immediately see some results. You can see the capillary rise starting to take effect here. Okay, this first run is complete, and let's preview these things. So looking at it as a movie, you can see that even though the rate of increase is slowing, I measured it and we're only at about a capillary rise of 35 right now. We expect about 50. So what I'm going to do is increase the number of time steps, and then we'll look at it after this version of it runs. So the number of time steps per frame increases by a factor of 10. Okay, we have new results at a much longer time scale, or a longer time period, and you can see that this one is almost at full rise, and then finally these are basically stable after that. So let's pick this last one and get a measurement of the capillary rise. This isn't perfect because ideally the domain would have been wider so that this is not, so this truly reaches a flat pool level. It's arguable that it wasn't big enough here. But anyway, let's put in a line from about the middle of the meniscus here. Let's measure up from here. Right to there is 55 lattice units, so I'd say it's a pretty good success according to the expectations. It's far better than what's in the book, incidentally, and that's because the book failed to recognize that we can't really neglect the density of the vapor phase in this case. So, for instance, in equation 87 in the book, we should be using the difference between the two densities instead of the density of the liquid, as one would do when with comparing like air and water. One neglects the density of the air. So the difference in intensity is actually about 440, and that should give a quite nice result for this.